So last time, I'm not going to assume much about last time. We're going to repeat some things, so I hope that will be helpful. This theory is about objects of the following form. So we look at powers of an object, certain real valued properties of those, and then we normalize and go to infinity. And we looked at some examples last time. The first example that I gave was matrix multiplication. We're going to talk a lot about matrix multiplication today. The second one was Shannon capacity. The third example, which I'll also talk about today, if we get there, is about cap sets. The fourth example is about sunflowers. And the fifth example was about quantum entanglement. So we'll be talking about this one mostly, and hopefully a bit about those two as well. Okay? Right, so let's start at the beginning again. So I want to talk about matrix multiplication. Let me just repeat the problem. So what is this problem about? We're given two large matrices, and we want to multiply them, right? So n by n matrices. We want to multiply these matrices, and the question is how many scalar operations plus and times are required to do this. And if you follow the algorithm that you would usually do by hand, you would get something like 2 times n cubed operations. And it's not hard to see that you require at least n squared operations. So it will lie somewhere between these two functions. And we'll simplify this problem. Yes, Ryan?
We can't rule out the case that there's some fast algorithm that does something that doesn't use additional multiplication. Right? Like it could be true that we need, n to the alpha operations, but there's actually somehow an algorithm that just is like quadratic times Polytope or something, right?
I missed the question. Sorry. The question is it?
It could be true that you require n to the alpha operations for some alpha bigger than 2, but there's some algorithm that magically gets n squared Polytope, right? Like this is not a lower bound on the runtime. You could do something else that doesn't use scalar operations.
Yeah, there could be some. Yeah, I'm not talking about Turing machines. That's what you're saying, right? Yeah, that's right. So that's already the first simplification. We focus. It's an algebraic problem, and then we focus only on algebraic algorithms.
But morally, we think that the correct algorithm should be algebraic, right?
Maybe. Yeah.
Okay.
I'm not sure. I don't know if there's any. I don't know of any arguments for this, but yeah.
All the algorithms we found so far are algebraic.
That's true.
That's an argument.
I think that's true. Yeah.
Maybe
Yeah.
It's not. It's the kind of discussion you should have with data.
Right. Exactly. Yeah. So, and I'll simplify even more. So, yeah, algebraic algorithms, and then I only want to focus on the exponent. So, I want to focus on this exponent. The question is, what's the optimal exponent of n in the complexity of matrix multiplication, right? So we don't care about the constant in front, and so we know that this exponent has to be at least 2, and we know that it's at most 2.37. Right. So the upper bound comes from constructions of algorithms, and the lower bound comes from non-existence of algorithms, some kind of abstractions. And last time I gave a very quick history. I want to do this again. So a quick history of matrix multiplication algorithms in the form of of a graph over time. So the first non-trivial algorithm was discovered in the 60s, and this algorithm brought down the best upper bound on omega from 3 to 2.8. Right, and since then, there was a short pause here, and but since then this has been brought down. Let me just roughly sketch it to 2.37, as I said earlier. So the last improvements on this were like somewhere in the 2000s. And the lower bound, so this is the best upper, this is the curve of the best upper bound. The lower bound has remained 2. So what I want to talk about today is, if we focus on the methods that have been used to obtain these best upper bounds, we can explain why this graph has flattened. So that's what I want to talk about. We can prove a barrier. I can prove a lower bound if you use those methods. Yeah, so we're going to prove a barrier, like 2.16. Depends a bit on what methods you consider. So it says that if you use the methods that have been used for these upper bounds, then you cannot go below 2.16. So this is a barrier. All right. Okay, so how do we find algorithms? On a high level, the idea is that, and that's how I want to think about it today, is that it comes from a reduction. So there is the matrix multiplication problem. And when you construct an algorithm, you can think of it as a reduction to some kind of unit, some kind of natural unit problem. All right, so this is some kind of reduction. We're going to make this precise later. The point is that in practice, instead of doing a direct reduction like this, we do a reduction first to some intermediate problem. And then we reduce the intermediate problem to this unit problem, whatever that is. Okay. And the theorem that I want to prove, this is with Christandel and Frana, is that if you construct your algorithm like this, then there will be a barrier. So we will prove a barrier depending on the intermediate problem that you use. All right. So a barrier on the best upper bound on omega that you could obtain. There are similar results by Allman et al. I also mentioned that. All right. So now the next thing we should do. So this is very high level. So these problems correspond to tensors. So what I'm going to do next is talk about tensors. Thanks. 1L and 1N also. Okay, good, thanks. So let's talk about tensors, if there are no questions. And I want to talk about this asymptotic spectrum of tensors again. Asymptotic spectrum of tensors. Recall what we did last time. So a tensor is a three-dimensional array, right? So let's take two of them, T and S. Of some format, right? With some dimensions, not necessarily the same. And we defined this relation on these tensors. So we said T is at most S if there exist three matrices, A, B, C, such that I can obtain T from S by taking linear combinations of the slices of S in one direction according to A, linear combinations of the slices of S in the other direction according to B, and linear combinations of the slices of S in the last coordination according to C. So I want to write that as T equals A, B, C dot S, and maybe let me write it out again. So it's a sum over indices little a, little b, little c. A, IA, B, JB, C, KC, S, ABC. And this would be the ijkth coordinate of my tensor. All right. So this definition made a lot of sense because you can define the tensor rank with this notion. So the tensor rank is the minimum number n such that your tensor is smaller than the n by n by n diagonal tensor with ones on the main diagonal, which I denote like this. I don't know what I did last time. And then there's this opposite notion called subrank, denoted by Q, which is defined as the maximum number n, such that this n by n by n diagonal tensor is smaller than T. And we define the product of tensors and the direct sum. And we observe that that rank and subrank are not multiplicative under these under the multiplication. And therefore it makes a lot of sense to look at these asymptotic versions. So this is the asymptotic rank. Take the rank of T to the power n to the power 1 over n. You let n go to infinity. And we did the same thing for subrank. Right, so that's asymptotic rank and asymptotic subrank. The general picture was that we have subrank and rank. Of course, they lie like this. And the asymptotic subrank and the asymptotic rank lie in between like this. Right? And then we define this set X. This is going to be useful today. So X, the asymptotic spectrum of tensors, is the set of all maps phi from tensors to non-negative real numbers with 4 properties. So we want this map to be, we want phi to be multiplicative. So for any s and t, any tensors s and t, I want phi of s times t to be equal to phi of s times phi of t. I want phi of s plus t to be equal to phi of s plus phi of t. We wanted phi to be normalized on these diagonal, these n by n by n diagonal tensors. And the 4th property is that if for any s and t, if s is smaller than t, in the way we defined it before, then I want phi of s to be smaller than phi of t. Yeah, so a simple set of rules that these phis have to obey. It's completely unclear now what x is, right? But it's not hard to see how you could use such an x, set x. I stated that as a lemma last time. So if you take any phi in x, then you can use this phi to upper bound asymptotic subrank and lower bound asymptotic rank. That's a simple statement, simple to prove also. And the non-trivial statement is that this tool is optimal. Like this tool is sufficient. It's a complete tool. In the sense that if you fix your t and you minimize over all these phi in x, then you'll actually reach the asymptotic subrank. And the same for asymptotic rank, but there you need to maximize. Okay. And what makes this statement extra interesting is that the asymptotic subrank and asymptotic rank are themselves not in X. We talked last time about how, even if you don't know what's in X, how this tells you something about the behavior of asymptotic subrank and asymptotic rank. Today we're actually going to see some elements in X. But first I want to talk about these barriers again.
Can I ask a question?
Yeah.
The first one is, if I know the minimizer that gives me the asymptotic subrank, can I then construct the maximizer?
Ooh.
Some sort of duality that would do this?
No, I've no idea. No, I don't know. I don't
The
know.
other one is, say you took a limit there of the rank of t to the tensor n.
Yeah.
Do I know that that sequence is monotonic?
Yeah. So the idea here is it's tensor rank is submultiplicative. It will not be monotonic, but it will be eventually, in some sense, monotonic. Yeah, it's submultiplicative and bounded. And then, if you have an expression like this, and this is submultiplicative and bounded, then it becomes an infimum. Yeah, yeah. Ryan?
Well, we need the action of choice to construct something that's actually in this.
Is it a question?
Yes.
So, yes. Well, I can tell you that the proof of this theorem uses the axiom of choice. But I don't know. Our construction, I don't know. I'm not.
This proof X is not empty.
Well, this proves it's not empty. Yeah.
Okay, you need choice.
It's used in there. Yeah, definitely.
Okay.
In our construction, I think it's not used. Not entirely sure. No,
Okay.
I don't think it's used there. Yeah. Yeah. I can imagine that in specific cases you don't need the axiom of choice. For tensors, I'm not sure. All right. Good. So, yeah, let's go back to this. So we had this high-level idea of how algorithms are constructed, namely via intermediate problems. And so let's make this mathematical. So this is the third part, barriers. So the first thing, so I told you before, problems correspond to tensors. So the first thing we have to do is talk about the matrix multiplication problem. It corresponds to the matrix multiplication tensor. So that tensor is denoted by MMM for multiplying two m by m matrices. And it's this tensor. You sum over ijk from 1 to m. And then you take this outer product of 3 basis vectors. So this tensor, let me first write where this tensor lives. It lives in f m squared, m squared, m squared. So eij is a vector of length m squared with a single 1 in it, and the rest is 0. And these are the same. These are similar, and then you take their outer product to get like a 3-dimensional array. Okay. That's the definition of the tensor. So this reduction that I was talking about, it looks as follows. Let's take m to be a power of 2 just to make things a little bit easier. What you want to do is you want to look at this matrix multiplication tensor, and we want to prove an inequality with, on the right-hand side, a diagonal tensor. Let's say this diagonal tensor is of size 2 to the power gamma n plus lambda over n. Now with this inequality as we defined for tensors, right? If we prove such an inequality, then we get that omega is at most gamma, and this is in fact almost equal to the definition, right? So I claim that this is really the definition of omega. Yeah. So this is the definition of omega, but in practice, let me first simplify this a little bit. So matrix multiplication tensors have a nice property that they multiply in the following sense. So this tensor is actually equal to the nth power of the smallest matrix multiplication tensor, so the 2 by 2 matrix multiplication tensor. And the same holds for these diagonal tensors. So this right-hand side is actually this tensor power of the smallest non-trivial diagonal tensor. Right, so this is the same. This is the same statement. And now, so what happens in practice? To get the best upper bounds, you take a large power of the matrix multiplication tensor, and you prove an inequality that looks as follows. You have some tensor to the power, let's say, alpha times n over here. And then you have another inequality with the diagonal tensor. All right, so that's, yeah?
Can you remind us how these two are equivalent, the omega and Polytope?
This guy?
Yeah.
So I think, I'm not sure what I think last time I explained, I think I never really explained it, but rank upper bounds for matrix multiplication correspond to algorithms. That's the idea. So if you look at the rank of the MMM matrix multiplication tensor, the tensor rank, then this is equal to the complexity, like the algebraic complexity of matrix multiplication up to some factor 2 or something. I claim. And so there is something non-trivial going on here. So the algebraic complexity is like the circuit complexity, right? It's algebraic circuit complexity. The rank a priori corresponds to the size of a bilinear circuit. If you would unfold the definition, you would see that it corresponds to the size of a bilinear circuit that computes the... So one way to think of tensor rank is that it's the smallest number R, such that you can write your tensor as a sum of simple tensors. That's the same as what I've been doing there, but it's maybe nicer here. So simple tensors are tensors of the form ui tensor vi tensor wi. So ui is a vector, vi is a vector, wi is a vector. And we take their outer product again. Now, suppose you're given such a decomposition, then I want to turn it into a circuit, right? An algebraic circuit. And the way it works is you take one of these summons. I want to think of somehow you want to think of these as your corresponding to the input. And this guy, in some sense, corresponds to the output of matrix multiplication. So I'm multiplying A and B, right? And I'm getting some output C. This guy tells me, so this is a vector. It tells me which elements to take in my input matrix. I take a linear combination of them according to this vector. I do the same with elements from B. I take their product. So I take linear combination, take their product. And then Wi tells me where to store this product in the output matrix. So it tells me multiply it with this constant and put it there in the output matrix. So yeah, and this is the connection. This is how you do it. So that's kind of the easy direction. I think the hard direction is to prove that this is actually that if you have a general algebraic circuit, that you can always turn it into a bilinear circuit with a constant overhead. Yeah, you have your circuit. You want to layer it, so you want to think of it as having plus layer, times layer, plus layer. And then you need to argue. So the problem itself is it's a bilinear problem, right? In the sense that it's linear in this guy and it's linear in this guy. Now you need to argue that you only need 3 layers. I'm not entirely sure how to quickly explain this, but yeah. This is a general fact about bilinear problems. That it's enough to look at bilinear algorithms. All right.
And when you say algebraic complexity, it means that you'll be knowing bit lengths or whatever?
Oh yeah. And it's just plus and times. Yeah, you can use like crazy constants in your algorithm as well. It's not clear that's going to be useful, but some crazy numbers you could use them with crazy bit lengths. Yeah, yeah, definitely. All right. So in practice, we do this, and this will give us an upper bound of alpha times beta. Right, so I'm just going via this tensor, but in the end I obtain an upper bound of the form we had before, and I get this coefficient alpha beta here, and this will be my upper bound on omega. Okay. And right. So let's move on.
I guess so this is implicit in what you were saying earlier, but just to confirm, so if I take the matrix multiplication tensor and like partially evaluate it on A and B, I get out C. Is that what you said?
Say it again.
If I take the matrix multiplication tensor and like partially evaluate it on A and B, in the way that you can take a tensor and like plug in one vector, like another vector, and then get out a single vector, then I get out C. Is that correct?
Yeah, so you're talking about it like you're doing a contraction.
Yeah.
Yeah, that's right. So if you have, yeah, that's a good way. So, well, yeah, you can think about it like that. You can also say, that's, I mean, yeah, that would work, yeah. Yeah. All right. So let me tell you which T people use. So the T people use is called the Coppersmith-Winograd tensor. It's actually a family. And it looks somewhat like this. It's a sum I equals 1 to q of E0, EI, EI plus E0, E0, E1, and then all permutations of these terms. Permutations meaning permuting the tensor legs, right? So this is the guy that's used in the best upper bounds. The guy that's used to get omega at most 2.37. I'm not going to explain how we do this. I just want you to believe that this is the guy. And sorry?
Like there should be E0, E0, EI. Second.
No, this is what I want.
After that.
E0, EI, EI, and here I have 0, 0, 1.
0, 0, 1.
Does that make sense?
0, 0, I.
It's funny, maybe it should be actually q plus 1. Yeah, that was incorrect. I think it should be q plus 1. Thanks.
So you're telling me fix E0, 0, EQ plus 1 term for every I between 1 and Q, or is that?
No, let's just do this. Yeah.
Oh.
Yeah. Thanks. Yeah.
Good.
Right. So the statement is that if you use this T, then we get at best an upper bound of 2.16. In other words, if you right through this method, in other words, alpha times beta will be at least 2.16, whatever you do. And this statement comes from a more general statement, which is as follows. If you use some T, so with some general intermediate tensor T, we get at best an upper bound on omega of 2 times the logarithm of the asymptotic rank of T divided by the logarithm of the asymptotic subrank of T. Right, so that's why I wanted to define these asymptotic rank and asymptotic subrank again. These are what gives you the barrier. So if you use a T where the asymptotic rank and asymptotic subrank are very far apart, then this T is not going to be good if you aim for omega, if you aim for proving that omega equals 2. Right? So let's talk a little bit about the proof of this, which is actually pretty simple. And it starts with a lemma about the matrix multiplication tensor, and this lemma says that the asymptotic subrank of the smallest matrix multiplication tensor is actually known, and it equals 4. Right? So the asymptotic rank is not known because it equals 2 to the power omega, but the asymptotic rank, the asymptotic subrank is actually known, and it's 4. And I'm not going to explain now where this comes from exactly, but let me just say that this follows from, if you want to prove this, you can use Behrens sets So these are 3-term arithmetic progression-free sets in ZPZ. They appear in the Roussat-Semeredi problem. So yeah, they allow you to prove this. Okay. It's a combinatorial construction. And we'll come back to these types of constructions later on. So now with this lemma, we can see how you get this barrier. And it's actually pretty simple. So let's, right, the starting point is an inequality like this, because this is what we're going to prove barriers for. So we start with this inequality for some given t. And now we look at the first inequality, and we apply asymptotic subrank to both sides. Asymptotic subrank is also a monotone function, so that we can just apply it. Let's do that. And asymptotic subrank, it's not multiplicative, but it's multiplicative on powers. That's because that's kind of the definition. Kind of by construction, it's multiplicative on powers. So we can take these outside, these powers, n and alpha n. And then if we know what the value is at the left-hand side, it's 4. And then I want to take logarithms and take things to the other side to arrive at an inequality 2 over the logarithm of the asymptotic subrank of t is at least alpha. Right, so that's the first thing we know. Then so it's at so alpha is at least 2 over the logarithm of the asymptotic subrank. Now we look at the other inequality over here, and we apply asymptotic rank. So we do the same thing. We get that the asymptotic rank of t to the power alpha n, let me write, is at most 2 to the power alpha beta n, plus little of n, which I'm just ignoring now. And if we rewrite this, we get that the logarithm of the asymptotic rank of t is at least beta. Right, and now I just combine these two bounds, and I get my lower bound on alpha times beta. Yeah, so that's it. So that's just rewriting things. Right. So that's good. So we have the general theorem, and now I want to talk about how we get like the numerical barrier, right? So we have the general theorem. How would you get like numbers like this, 2.16? That's the fourth part, tools. So here we use our set X. So what we want is functions phi between the asymptotic subrank and the asymptotic rank. And we know that we get this if we take any phi in our set X. Right, and then we try to find a phi that becomes very small, and we try to find a phi that becomes very big, so that we can actually separate these two, asymptotic rank and asymptotic subrank, so that we get a barrier. And last time I mentioned 3 elements in X. They were the flattening ranks, so let me write them as R1, R2, and R3. So how find those? So you take your tensor and you group two of the indices together to make it a matrix. And then you take the matrix rank. Okay, that will be one of the flattening ranks. And the others you get by grouping the other elements, the other indices together. So it's not hard to see that these are an X. And these are very useful for lower bounding asymptotic rank. Actually, they are the best elements we know to lower bound asymptotic rank. We don't have any separation between those. And what I want to talk about today is a family of elements denoted by f theta. I call them the quantum functions. They are a family. They are parametrized by this parameter theta, and they are in X for complex tensors, so tensors over the complex numbers. Then the third thing I want to talk about here is what's called the Strassen functions. It's denoted by zeta theta. They are not in the asymptotic spectrum of tensors, but they do give upper bounds on asymptotic subrank. Okay. So this uses representation theory. This is more combinatorial. So the third one is easier to understand. Right. So this is a theorem again by the same authors. This is much older. This is by Strassen. Right. And maybe what's nice before we have a break is to say that you can think of, if we write down this flattening ranks as points on the board, you can think of these functions as some kind of interpolations between the flattening ranks. So depending on the theta that you pick, you get an element here somehow in the some kind of interpolated element, an element interpolated between the flattening ranks. So it's not an average or anything, but it's an interesting. So there are values for theta that you can pick to get the flattening ranks. Okay, so let's take a break. Let's take a break for 15 minutes and then do a head count. Let's continue. Okay, good. So I was talking about these tools, and I want to start with talking about these quantum functions and give you an idea of how you make them. So let's start maybe on the board here. Quantum functions. Why are they called quantum functions? Because we were inspired by this from quantum information theory. So the statement is that these are elements in the asymptotic spectrum, but I haven't defined them yet. So what I want to use is the entropy function. Which probably many of you know. So let me just write it down. So P is a probability distribution, or probability vector of length d. So they sum up to 1, and these are real numbers, at least 0. Then the Shannon entropy of this vector is defined as minus the sum of pi log pi. And the way this shows up in our construction is that the Shannon entropy gives tells us how multinomial coefficients grow. So if I take a multinomial coefficient, so let's say that all the pi's are divisible by n, then in the sense that if I multiply them by n, they become natural numbers, then I can look at the multinomial coefficient like this. And then we see that this is at most, or you can prove that this is at most 2 to the power n times the Shannon entropy of P, and it's also at least 2 to the power n times the Shannon entropy of P minus little of n. So the Shannon entropy tells us how these multinomial coefficients grow asymptotically. Now, the next thing I need is something called a moment polytope. Which is a pretty complicated object, and I will give you a very concrete description of it, as concrete as I can make it. So let's take a tensor S. This is a complex tensor. What I'm doing here works only over the complex numbers. Size d1 by d2 by d3. We flatten this tensor in the way I explained before. Let's take the first flattening. So I just group 2 of the indices together. It becomes a matrix. We now take of this matrix the singular values. Let me call them sigma 1, sigma 2, etc. up to sigma d1. So these are non-negative real numbers. I've ordered them like this. And I want to turn this into a probability vector by squaring and then normalizing. So I take my singular values, I square them, and I divide by their sum. Right? Okay. So now the moment polytope of a fixed tensor T denoted by P of T is the following set of triples. Let me give this a name. So let's call this vector something like, this is made up, the spectrum of S1. Then I look at the triples, spec of S1, spec of S2, spec of S3, triple, where I go over all S that are smaller than T. Yeah, so T is fixed. I go over all S that are smaller. Let's say in the same space as that T lives in. And then I look at these triples of probability vectors that I get by looking at the singular values of the flattenings. Yeah. So pretty complicated object. Actually, you need to do a little bit more. You need to look at limits as well. So I do something like this. Doesn't really matter. A complicated set. And it turns out to be a polytope, which is also completely non-trivial. All right. So that's the moment polytope. Let me tell you now how you make this quantum functional. Sorry? Yeah, I'm not sure. I'm not sure if that's true. Yeah, I'm not sure. I know this works. I'm not entirely sure. What is true is that if you take, there's this alternative description in terms of like Schur-Weyl duality. If you take, maybe I'll mention it quickly. There's this Schur-Weyl characterization where you look at your tensor T, you take it to the power n, and then you decompose this tensor according to the Schur-Weyl duality decomposition. So you can write it as a direct sum of tensors that are labeled by triples of partitions. This only makes sense if you know Schur-Weyl duality, but there is a very natural decomposition. And so these are partitions of n, triples of partitions of n, and then an alternative, which is also very magical, an alternative description of this moment polytope is that it's the closure, like in Euclidean space, of the set of, so you look at these lambda mu nus that are, and we normalize them. And we take only the lambda mu nus for which these components are non-zero. So that's the alternative description. And yeah.
Something a little strange. What is lambda? It's a partition.
Yeah, lambda is a partition of n.
About its length. There's nothing about its length.
Yeah, there is, but yeah, there is. I mean, it's a partition of n of length at most the dimension of t. Yeah.
That just has to.
Yeah. So there is a deep connection going on over here where you have, and this is actually important in the proof, but I'm not going to do it. So this is important in the proof that these elements are in X. There are two ways of characterizing this polytope, and this is one, and this is the other. All right.
Does this other one even work with arbitrary fields because except the decomposition, there doesn't seem any mention of C anywhere?
Yeah. So this only makes sense over C. Yeah, that's right. So far, and there could very well be a way of extending it to other fields. I just don't know. Yeah, I think it would be very interesting to do that. Yeah.
Sorry, is it like maybe just something obvious? Is there like a quick way to see that like even the types match up? Because I mean, this looks like a polytope where all these specs are vectors of like D1, D2, D3.
Right. So in this decomposition, the partitions will have that restriction that they have at most D1 parts.
Oh, okay.
Yeah.
Oh, okay. Okay, fine.
Right. Thanks. Good. Yeah. So let me now just state how you make these quantum functions. So it works as follows. Yeah.
What else can you say about this? Why is it called a moment polytope?
It's called a moment polytope because the origin of it is related to something called a moment map. So this is, yeah. So this appears in physics. That's really where the word comes from moment or momentum. And I don't know much about that at all, but that's somewhat the origin of the word. So it's the image of a moment map, and this has its origin in physics. Yeah.
So it's just very, looks very mysterious.
Yeah, and it is very mysterious, and it's mysterious for everyone. We don't know how to compute these objects, or like we don't know. Yeah. Avi has these algorithms, these scaling algorithms, which are related to these objects because they they decide membership in a certain way of such polytopes. So that's like ongoing work, like the algorithms that.
So if I should just say, so this to any tensor S, the tuple, so this is the moment map.
Okay.
Okay.
And
And
why
yeah,
care
different
about
story.
it? Or?
I think the hardest part is to understand why this is a polytope.
Yeah. Oh, but although we don't.
Define a map in whatever way you want. Here is one map that I defined, which is called the moment.
Right,
Obviously, it's on this.
Maybe say something like why define this way?
Oh, why define it this way?
Yeah.
This happens to be the gradient of the group action.
No.
The gradient of the group action.
The gradient with
group
respect
is
to the
what? The ABC?
The group will be GL cross GL cross GL.
Cross GL.
Yes. And then you have to do a certain quotient thing.
Right. So yeah, it becomes complicated.
Okay.
Here's one question.
Yeah.
If T is a symmetric tensor,
Mm.
like, is it just as good to take S as symmetric as well, and then just look at like Z points?
We don't know. And yeah, in general, we don't know much about. So if you could try to do the whole thing for symmetric tensors, and then you can say maybe you define the restriction to be also symmetric. So you just focus on symmetric tensors. I think the whole theory works. Also, these elements will still be in that spectrum that you get, the asymptotic spectrum. But you would expect maybe that there are more elements, and we don't know anything about how you would get more. Yeah. Actually, making progress there might be interesting, or should be interesting, for if you want to make progress on the capset problem or other problems in combinatorics, because these usually talk about actually the symmetric problem, but what we actually prove is something about the multicolored version. Some of this difference is related to whether you look at symmetric tensors or not. Yeah. Let me write down what the quantum function is, just so that you have seen it. So the parameter that I've been talking about is a probability vector of size of length 3. And then for any tensor T, the definition of this function on T is as follows. It's a supremum of 2 to the power a weighted average, a theta weighted average of the Shannon entropy of a vector xi, where I go over triples x1, x2, x3 of probability vectors in my moment polytope. Okay, so we have this complicated polytope, and then we are optimizing a kind of a nice function over it because it's a concave function, and that's the quantum function. And we proved that this function is multiplicative, etc., using ideas from representation theory. I will not go into that. I want to talk a little bit about a simpler object, namely these Strassen functions. So these quantum functions, I think they're mathematically very nice, and they actually give these points in the asymptotic spectrum. This is kind of the state of the art. We don't know any other elements in the asymptotic spectrum. The Strassen functions are slightly easier to understand, and they work over all fields. And they give us upper bounds on Q tilde. So that's good for us if we care about, for example, barriers. Okay, so let's go there.
I have one question.
Yeah.
So with these quantum functions, I mean, you said that they're somehow interpolating between R1, R2, and R3.
Yeah.
But I don't even see how any of these RIs are.
So my claim is that if you take
You like fix theta 1 to be 1 or something.
Yeah.
It should be R1, but
exactly.
then you get like 2 to an the soup over this moment probably too clear.
Yeah, it's not immediately clear. You have to argue, but it will not be hard to prove it. You don't need anything. I mean, it's enough. What's on the board should be enough to prove it. I think
So
you want to.
because like the rank is related to the number of singular values.
Yeah.
I see.
Yeah, that's how it goes. Yeah, that's right. Yeah, I hope it gives you a taste somehow. It's also, it's hard to explain more about this, and I will not do it. I hope it gives you some taste of what's going on there, what kind of objects are playing a role there. Right. Let's see if we can understand more about these Strassen functions. And also I wanted to mention it because there are many open problems there. So one of them is to actually make this work over other fields or other characteristics. Algebraically closed, but finite characteristic, positive characteristic. Right.
Is there some alternative description of that set in terms of those multinomial things?
Of this set?
No, the F theta set.
An alternative description of this set?
Yeah, in terms of like some kind of multinomial.
Not sure. No. Not sure. Okay. Strassen functions. He calls them upper support functionals, by the way. We start with a tensor T over some arbitrary field of dimension, let's say n1 by n2 by n3. And we're going to talk a lot about the support of this tensor. So the support is just a set of triples of indices ijk where this tensor is non-zero. All right, so this is a subset of triples. It lies in this product set. And the Strassen function zeta theta on T is defined as follows. We first minimize over all tensors S that are isomorphic to T. I want you to just think of isomorphic as that this inequality goes both ways. That's what it means. And then we maximize again this weighted average, theta weighted average of certain Shannon entropies, and this time it will be the following. It will be a marginal distribution of some probability distribution P from the set of all probability distributions on the support of S. Okay, so we start with T. We look at all tensors S that are isomorphic that we can obtain by doing a basis transformation. And then we maximize this weighted average of Shannon entropies of the three marginal distributions of any P probability distribution on the support of S. The support of S is a set of triples, right? So you have a probability distribution on a set of triples, and then you have three marginal distributions by focusing on one of the one of the factors, right, of these triples. So this is the definition. It's much simpler because, well, I don't know, I think this is much simpler to understand what's happening here. And so here the result is that this is not in the asymptotic spectrum, but it's almost. So what happens is that this function is submultiplicative for any theta. It's additive, it's monotone, and it's normalized. Okay, so it has all the properties except for being supermultiplicative. But these properties are enough to give that the asymptotic subrank is at most this Strassen function. All right. Let's do one example. And this example is the W tensor that we've seen before. I use this tensor to say that asymptotic like rank and asymptotic subrank and subrank, that there are all like different notions. So it was this tensor, W is, let's write E1, E1, E2, plus the 3 permutations. So E1, E2, E1, and E2, E1, E1. Now, we're interested in the asymptotic subrank of this tensor. And I'm now just assuming the theorem. So we know that this will be upper bounded by this Strassen function. It turns out that for this guy, we don't have to take any other s. We can just stick to t. Anyway, if we're looking for upper bounds, and since this is a minimum, we can always take the tensor itself. This is really the complicated part of this function. Like, it's completely unclear how to ever minimize over this. That's like completely unclear. This is easy once you fix s, because this, if you know what this set is, it's like a convex set, and you have this concave function. This you throw in a computer, and it will give you the answer numerically, or you could even do it by hand sometimes. So here I just pick W as my t, as my s also, and then it turns out that the maximum is achieved by the uniform probability distribution P. So I'm not going to prove this to you, but it turns out that you want to take the uniform probability distribution, and then the value you get is this sum of Shannon entropies. So you have to look at the marginals, and they will turn out to be like 1/3, 2/3, because it's like if like 1/3 of 2s and 2/3 of 1s in each term. That's how it happens. And this will give you 1.88. All right. I have another example that I want to mention. This is a tensor T, and it's defined as follows. I take E1, 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 E2, 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 and E3, 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 plus E1, E2, E3, plus all the permutations of these guys. Yeah?
Does that 1.88 have anything to do with like the fact that the best back for addition variety is something like 1.88?
Yes.
Okay, it's the same 1.88.
It's the same bound, yeah.
Uh-huh.
Yeah. If you reach the end, then you'll see roughly how this goes. Yeah.
Uh-huh.
Yeah.
Cool.
That's why I gave the example. So this, you could think of this as like the sunflower tensor, if you want. And that tensor is like the capset tensor. So what happens with this tensor? So, okay, it's a tensor. I want to think of this tensor as a tensor over the field F3. So how does that make a difference which field I pick? Well, it makes a difference in this minimization, because when I talk about S that are isomorphic to T, this depends on which field I'm working over, right? Because that tells me like what kind of basis transformations I can do. And so here, again, I'm interested in the asymptotic subrank of T. And we're going to upper bound this with the support function. Again, I pick the uniform theta. And now it turns out that if you do a very clever basis transformation, so before we didn't do any basis transformation, here we actually do need to do a clever basis transformation over F3. Then it turns out you can get a non-trivial upper bound on this, and this basis transformation was observed by Terence Tao when he wrote about the capset problem on his blog. Okay. Good. And here we see why. So if you would do this over the complex numbers, you wouldn't get any interesting bound here. It would just be 3, because this tensor over the complex numbers is isomorphic to a diagonal tensor, actually. All right. Okay, good. So I want to give some intuition for the support for the Strassen function. Let's see if we can do that. Let's do this cleverly. So let's do it over here. Because for the quantum function, we didn't get much intuition, I think. So maybe here I can do something. All right. So let's see if we can do a proof sketch of the fact that the asymptotic subrank is upper bounded by this Strassen function. And I want to give this proof sketch via one of the notions that Terence Tao introduced, which is called slice rank. So let's try this. So first I want to define slice rank of a tensor. It's a nice definition, and I also wonder if there's like a more general notion of slice rank in like all the other settings that you could think of in the context of asymptotic spectra. For tensors, it's defined as follows. It's a minimization of the sum of flattening ranks of tensors x, y, and z, such that t equals x, y, z. So I'm summing over. So I have t's fixed. I go over all tensors x, y, z that sum to t, not direct sum, just normal sum. So element-wise sum. And then I look at the sum of the flattening ranks. So x, I take the first flattening rank, y, the second flattening rank, and z, the third flattening rank. And then you try to minimize this sum. Yeah, that's the slice rank. Yeah?
What about these flattening ranks? So you take the one you're going to.
Flattening rank means you have your tensor and you view it as a matrix. By grouping two of the indices together, of the three indices that you have 3 indices, you group 2 of them together and it becomes a matrix then. So if it's an n tensor, it becomes an n squared matrix. So
okay. Okay. So it's not a
yeah,
matrix.
you have your tensor and then you.
The rank of this n by n squared matrix.
Yeah.
Okay.
Right. So okay, this guy. Well, it's a nice function. You could wonder, is it maybe in the asymptotic spectrum or not? Well, it turns out that this guy it's not submultiplicative. And it's also not supermultiplicative. So it's kind of a complicated function. but we can say something about it asymptotically, and that's kind of the point of these Strassen functions. I'm gonna assume some facts. Terence Tao proved that the subrank of a tensor is at most a slice rank. This I want to assume, okay, for now in this talk. It's a very nice inductive proof on his blog. From this statement, it follows that if I'm interested in the asymptotic subrank, and I take it to the power n, this n I can put inside or outside, doesn't matter, then this is at most the slice rank of t to the power n. That's a trivial consequence of the first line. Now the statement I want to talk about is this one. I can upper bound this slice rank of this power using the support function, the Strassen function, sorry. So the third thing is what I want to talk about. All right. Yeah. Sorry, yeah, there's something missing. Thanks. Yeah. So it gives the rate of growth of the slice rank when you take large powers of your tensor. Okay, good. So okay, let's see if I can explain this. So okay, what was the definition? It's not. It's still here. Well, let me write it down. So it's well, we had to minimize over S isomorphic to T, and then maximize over probability distributions on the support of S. And then what we're actually looking at is this function, this 2 to the power the weighted average of the Shannon entropies of the marginal distributions. So let's take S optimal. So let's take S, that is the minimizer of my minimization, and let's take P, that is the maximizer. Now what we do is we take our S and we simply write it down in the standard basis. So I go over all ABC in the support of S. And I have as a coefficient SABC, and as a basis element I have EA, EB, and EC. Right? Just wrote down S. But I only have to go over the support. That's the definition of support. Now we're interested in powers. So I want to look at S to the power n. And I start with this. So if I take this right-hand side to the power n, I'll get a sum over indices A that are now n-tuples, and B also n-tuples, and C n-tuples. And this is the definition of taking the power. I get here a product, A1, SA1, B1, C1, dot, 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 S, A, N, B, N, C, N. And here I get like products of the basis elements. So E, A1, E, A, N, EB1 up to EBN, and EC1 up to ECN. Okay. So that's my power. Now, look at one of the summands in this big sum. So I want to think of each summand as, so each summand corresponds to taking n samples from the support of S. Right, so these samples are like A1, B1, C1, that's the first sample, to AN, BN, CN. I want to think about this differently. I want to think of the triple ABC. So A is an n vector, B is an n vector, C is an n vector, as an empirical distribution on the support of S. And then I can focus on one of the three factors. And that corresponds to a marginal distribution. So I want to think of A, which is like A1, A2 to AN, and also the other guys, B and C, as marginal distributions. Then, if we look at the Shannon entropy of A and the Shannon entropy of B and the Shannon entropy of C, then I want to put OR here. So one of them, at least one of them, has to be at most this weighted average, this theta weighted average of the HPIs. Why is that? Because we chose the distribution P to be a maximizer of this weighted average of marginal distributions on the support of S. Yeah, so it's a maximizer, which means exactly that it has to upper bound at least one of them. It has to upper bound the weighted average, and then it has to upper bound at least one of them. All right, good. So now we get to the point. So again, S to the power n. We wrote it as a big sum. I now want to write this as a sum of three big sums. And the idea is that of the first sum, the first flattening rank will be small. Of the second sum, the second flattening rank will be small. And of the third sum, the third flattening rank will be small. So we take the big sum and we kind of go over subsets of the triples ABC. So what we do here is we go over the ABC for which the Shannon entropy of A is smaller than this weighted average. Here we do the same, but we want that B, the H of B, is small. Here we do the same, but we want that the H of C is small. Then And here this is the same, like we put the same summand over here as we did there. Then, because of this statement over here, we know that we have at least covered all the summands. It could be that there's a triple that occurs in multiple, then we just ignore one of them. We just make sure it's in exactly one sum. Then, my claim is that if I look at this guy over here, and I look at the R1 of this, I claim it's small. And the reason this happens is that the entropy of A is small, like the entropy of the first factor. So there aren't many, so not many A's appear. So to make this a little bit more precise, this R1 will be upper bounded by the number of elements A, the number of n tuples A, for which the entropy is at most this weighted Shannon entropy. Okay, I claim this. And then if you start upper bounding this size, you'll get that this is at most some polynomial factor in n times 2 to the n times this weighted average. Right, which was which equals some poly n times our Strassen function. So that's upper bounds the first part. So we can upper bound the R1 of the first part by, should be to the power n again, by the Strassen function, and we can do the same for the other parts. And this upper bounds the slice rank of this nth power. Okay, so that's. I hope this gives some idea of where this comes from. All right. Any questions about this? There are lots of things known about how the support functions and the Strassen functions and the quantum functions relate to each other. But maybe what I want to talk about is a little bit about these combinatorial problems. So let's do that. Okay.
So this final inequality that you have is like a purely combinatorial thing.
This guy, or this right.
This is purely combinatorial.
Yeah. 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 It's just about counting these strings. Mm-hmm. Yeah. All right. Let's talk about the final part. Combinatorial problems. What it's actually about is, maybe it's better to call it asymptotic induced matchings. All right. So I want to move, we did this before, I want to move from looking at tensors to looking at their supports. And I want to look at the combinatorial notion of subrank for tensors, but then for supports. So, and that will be the matching number. And the reason I want to look at these things is that you can phrase, or you can upper bound or study problems like the capset problem and the sunflower problem in this language. Okay. So the objects I want to look at are hypergraphs, or 3 graphs. And they're simply subsets of a product set, a finite product set. So V1, V2, V3 are finite sets. And look at subset phi. Of course, phi are also supports of tensors, so that's kind of the link I'm trying to make here. And then we say that phi is a matching if the elements are disjoint. So if you take any 2 triples that are different, A and B in phi, then I want that for all I, AI is different from BI. Yeah, so it's just saying that all the edges are disjoint. So an example is, for example, this guy 1, 1, 1, 2, 2, 2, 3, 3, 3. That would be the simplest example. All right. Now, I want to talk about induced matchings. So we say that if you have 2 such guys, so you have a phi and a psi, and psi is a subset of phi, then we call this subset induced if psi equals phi intersected with the product of the marginal sets of the psis. So it's like, you should think of an induced subgraph. But we're talking here about these hypergraphs. So you have psi, you look at the marginal sets. Maybe let me write it down. Where psi I is simply all the AIs that appear in psi. So that's induced. And then the induced matching number, and I sometimes like to call it the subrank. So the subrank or induced matching number Q of phi is the size of the largest induced matching, right, in phi. All right. Now, I said I wanted to talk about asymptotic induced matching. So we define a product, a Kronecker product of these hypergraphs simply by taking triples of pairs. So I have here A1, B1, A2, B2, and A3, B3, where I go over all A in phi and all B in psi. That's my product. It's again a 3 graph. And then we consider the asymptotic induced matching number. You can guess the definition, so it's this limit of the subrank of phi to the n to the power 1 over n. All right? Let's motivate this. The first motivation is the capset problem. So here, let me remind you. So here we are looking at x, y, z in z3z to the n, and we say they form a line if for some u and v with v non-zero, we have that x, y, z equals u plus v, u plus 2v. Right, for some u and v with v non-zero. And then the goal is to upper bound the size of a subset S of Z3Z to the n that is line free. So can we upper bound the size of any such set? That's the problem. Now, here is a claim. If we look at this phi, so that's the triple 0, 0, 0, 1, 1, 1, 2, 2, 2, and then the permutations of 0, 1, 2. So this is my 3 graph, my hypergraph. Then the claim is if I have some S that's line free, then if I look at phi to the power n and I restrict this hypergraph to S, 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 so I only look at triples that are actually in S times S times S, then this is a matching. It's an induced matching of size of S. Okay, so this is the link I'm trying to make, and then we'll finish soon. So if you want to understand this problem, the capset problem, then your goal here should be to upper bound the asymptotic subrank of this specific small hypergraph phi. I have a second example with the sunflower problem. We're not going to do that. So let's continue with this example. This is our goal, trying to upper bound this guy. And of course, we are going to do this using these Strassen functions and using tensors. So how does that work?
You want to say that these triples in phi are like the one-dimensional lines or something?
Say it again?
I mean, at least 0, 1, 2 and the permutations are like lines.
Yeah,
Right?
which you want to avoid, yeah.
Thing.
So this is like, that's right. 0, 1, 2 is like a line, but like a line in dimension 1.
Like one coordinate.
Yeah, like in one coordinate. And then you take n coordinates, and you're a line if you're a line in all coordinates. So that's what you're trying to avoid. Yeah.
So phi to the n somehow encodes these lines. Well, except for
Yeah,
maybe,
yeah. Except for these guys.
Take these here, but these are like very few, so you don't care.
Yeah, so in the end, what happens is if you restrict, if S is line free, and you restrict to the triple, to this product, then you're only going to see triples that are made up of products of these 3 guys. Yeah, because those are the trivial lines. Those are just points. Right. So here's the missing link to tensors. If you have a tensor T, you look at its support, which is a 3 graph, and you look at its subrank, then this is a very specific way of looking at the subrank of T, so it gives us a lower bound. Or in the other direction, if we care about, if we have some hypergraph, we can make that has that as a support, and we want to upper bound its subrank, then we can study the subrank of that tensor. So that's the first thing. The second thing is that the support behaves well under this product. And then the third thing is that if I care about the asymptotic subrank of the support of T, then this is upper bounded by the asymptotic subrank of T. Yeah, so the first statement is easy to see. The second one is also by definition, and I think together they imply the third statement. So let's just assume this, and then I will finish with what I think is an interesting tool. And this has been the tool. This was used to prove the capsule problem. It's the following theorem. If you have a 3-graph phi and you're interested in its asymptotic subrank, maybe because you're interested in the capsule problem, then you can use the following upper bound. You pick a field, F, then you pick a tensor, T, over this field, and such that the support of T equals phi. And then you look at the asymptotic subrank of your tensor T. So it follows from the lemma that this inequality holds. And now, this we've been studying before, the asymptotic subrank of a tensor. So for this guy, you could use the Stassen functions again. And this will show you, this will prove you the well-known bound on the capsule problem. Right, I think that's it. Thanks.